Hello, this is Jeffrey Fox with the second lesson, part B of the aspects of big data applications. A few remarks expanding our classification and categorization of big data problems. And here we just have a few remarks about NoSQL solutions. The end of the last lesson, we did the SQL solutions. So, of course, cloud software, what we're studying this course, came from the large internet tech companies like Google and Yahoo, and they needed cheaper and faster solution than relational databases. In this regard, I remember 20 years ago, I got some recognition, perhaps from Oracle itself, for being one of the first people to use relational databases to back-end web search. That wasn't a good idea, of course. All of this uses the large-scale commercial cloud or so-called public cloud infrastructure, which is dominated by Amazon, although Azure and Google and Rackspace, others are important. And Amazon has, of course, for example, allowed companies like Netflix to flexibly outsource their computing. This came together with a bunch of technologies such as Hadoop, which was developed at Yahoo, but based on MapReduce, which was invented by Google. This was an incredibly important driver, which I certainly didn't recognize early enough, and I didn't really understand properly why Hadoop was so important, because the MapReduce model is, in fact, the correct computing model for the dominant commercial applications like search and recommender engines. So Hadoop was developed by Apache, which is, of course, the topic of this course, and was perhaps one of the first huge successes of Apache in the big data area, and is probably responsible for the many other solutions of that type. Then we developed companies like Cloudera, Hortonworks, whose business model involves supporting and enhancing the Apache big data stack. Then on top of all Hadoop, of course, or actually below Hadoop, we had to have some data store where we developed NoSQL ideas, and that's typified by HBase based on Bigtable. So here we discuss HBase in a little more detail. Bigtable is famous. I mean, Google just publishes every now and then these incredibly influential papers, and they're revolutionary because Google has so much data and solves such big problems. If you solve something in Google, you're bound to solve a bigger problem than anybody else in the world. So HBase is built on HDFS, which is another entry in our software product table. There's the Hadoop file system, which I sometimes call a data parallel file system. It's the open source version of what originally is the Google file system. And it's the key features. The data is distributed over the same nodes that do the computing, and so we satisfy the important goal of bringing the computing to the data. So HDFS and HBase is equivalent to the stored data in a relational database, and MapReduce is equivalent to the SQL processing engine. And although it uses Java, not SQL, to express the processing in some sense. Hadoop is expressly designed to run in parallel, and you can argue, as I think I mentioned earlier, that the key advance that was encompassed in Hadoop and equivalent technologies was to expose the parallelism correctly in data systems. Previously, the parallelism had been locked up in a large commercial database or even an open source database, where the processing was so tightly integrated with the data storage, you could not expose the parallelism and exploit new techniques to make that run faster. So obviously, Hadoop has the map phase, which does the basics of searching, and say if it was doing search, and then the reduce phase, which integrates the results of the map phase together. If we look at eBay as an example of a discussion of what this debate between SQL and NoSQL, they have Hadoop for one type of application, which is built on HBase, Then Teradata, which is a data warehousing solution for different types of solution. And then some people use HBase, and some people use Cassandra or MongoDB. And it all depends on relative sizes and the nature, structure, how structured the data is. And as is not surprising, one size does not fit all. In this next little section, we just give a small example of parallel global machine learning. Remember, we'd introduced global machine learning, GML, as an important classification. So this is work in my research group and involves so-called multidimensional scaling, MDS, and clustering. These are two machine learning applications. Clustering does what it suggests. It finds collections of data that are near each other and associates them as a cluster. That's intuitively obvious. Multidimensional scaling takes data which could be in either an abstract data space because there were no vectors associated with it, or in a high-dimensional vector space, and it maps them to Euclidean space. In that way, if you actually start off with data in a high-dimensional Euclidean space, you talk of it reducing dimension, so it's dimension reduction technology. The reason why you reduce the dimension is to identify the key features. That sort of underlies all these technologies for latent factors and topics and things like that. But operationally, 3 dimensions is convenient because you can visualize things in 3 dimensions. So if you want to look at clustering, there is classically something called k-means that only works if you have vectors. There are other clustering algorithms which you could say are related to k-means, but they work for non-Euclidean spaces. And there are a whole set of actual clustering algorithms of different degrees of sophistication, and they make different underlying implicit assumptions as to the nature of the space. Gene sequences is an area we've done a lot of work. They have the feature they're not vectors. And there's no natural Euclidean space attached to them because each sequence is a different length. They're not easy to align with each other, at least not if you have a lot of them. But you can calculate using technologies originally developed by Smith and Waterman an estimate of the distance between them. And then multidimensional scaling maps points from original space to the Euclidean space, so distances in the mapped Euclidean space and near distances in the original space, whether those are Euclidean or not. We have technologies we built in-house on Azure, for example, which implement multidimensional scaling and k-means on Azure. Here's just a very simple example of a large cluster from a sample of 446,000 sequences. We have 128 clusters identified, colored. Of course, a given color is used more than once, and not 128 easy to distinguish colors. And we can look at that from all sorts of different points of view. Here's another view of the same data. And using a 3-dimensional view, you can browse through this data set and get a good feeling as to where really strong clusters are, like that or that, or where the cluster's a bit of a mess. Here's a bit of a mess. Here maybe is a bit of a mess. And you would know which clusters you could rely on better than other clusters. So in a lot of data analysis or data mining, humans are important because humans have intuition, and most intuition is best driven by images. The human ability to process images is very impressive. So now we come to some discussions about how to implement big data and what type of architectures are useful. And here we introduce an important analysis which underlies a lot of our work, which are the 5 different architectures, of which the first 4 are the most important, because the last architecture is a very special one. It's shared memory. If you look at parallelism, there are always 2 types of parallelism: distributed memory or shared nothing, and shared memory. Shared memory is what you see with a multi-core system. You have a bunch of parallel things sharing a common memory, and those types of architectures have very low latency, and they're typically done with threads. And there are some algorithms which are much easier to implement efficiently on shared memory than distributed memory. I should say that when we're discussing these architectures, we're not discussing all aspects of parallel computing, and things like workflow are orthogonal to these architectures. They're just discussing the sort of core parallelism which drives, which is going to dominate the performance of the algorithm. If we look at our applications, we had a whole bunch of pleasingly parallel ones, which included the many local machine learning ones. And we gave you examples where you had a whole bunch of images and you ran machine learning on each image separately, but the whole job was parallel. Here you can use Hadoop. Hadoop runs fine on these types of problems, but there are many other so-called high throughput computing or many task programming models. The second one, although I have search here, could maybe just better just be called MapReduce. It's the architecture, machine architecture, where you do not need iteration. It includes search, finding motifs or patterns, or collaborative filtering. That just needs one or two passes through the data set, and then that's it. There's an important architecture called Map Collective or Iterative MapReduce. There, that's where you see Hadoop with our technology HARP, our old system Twister, Twister for Azure, and now a dominant Apache system called Spark. So this is a machine architecture which supports the ability to run a map, then a reduce, then another map, then a reduce, with very low latency and low overhead between the different steps. Hadoop is, importantly, always writes things to disk, because that allows it to have a very robust, tolerant architecture, which allows jobs to run for different times without actually impacting the efficiency of the machine. That's because if you have independent maps and one map doesn't hold up the other maps, so the one map can write the disk, is completely done, and then you can reuse the node, and while you wait for the other maps to finish. In iterative problems, you can't reuse once a map is finished, it has to wait, that node which did that has to wait on all the other nodes. So iterative problems are much more sensitive to load imbalance, nodes taking different lengths of time, etc. The last set here is called map communication, corresponds to Giraffe, which runs iteratively. And here we have the same actually as map collective, except the communication is not collective, which means a communication that runs over the whole, a single communication over the whole set of nodes, but rather is so-called point-to-point. One task or process sends messages to another task or process, and a huge number of those point-to-point messages are done at the same time. These types of problems happen to be very sensitive to load imbalance, and you need to do very clever load balancing to get them to work well. Here we now have a couple of slides describing this from a more detailed. So here's classic MapReduce, which is, as it says here, of course, comes from commercial big data clouds, first Google and then Hadoop, the Yahoo version. You chop the data up, partition it, then you do a map, which converts the data, and then you take the results of the mapping and do a reduction operation using the key and the list of values to do that. So the implementation split up the data, they pass the maps to the reduction, They sort the inputs to the reduce function based on the keys, and they have quality of service and scheduling type technologies. Here's an example of iterative MapReduce. Here's our data stored on the disks or coming from instruments of various sorts. And then the data gets run through maps with different parts of the data stored on different disks going to different maps. Remember, we have HDFS where at least in the simplest model, data on disk 1 is computed by maps on the same computer as disk 1. And then we might go to another map, then another map, and then a reduction. And so here we have the definition of the map and the reduction. And that's shown a little differently here for MPI and iterative MapReduce, where we have a whole set of maps. In the case of MapReduce itself, you can have a few maps. But here you do MapReduce, MapReduce, MapReduce. Because when you have a few maps, you can just pipeline them together inside a single node and then write the answers to disk. In this case here, we have many reductions, maybe hundreds to tens of thousands in a realistic problem. And in order to make that run efficiently, you have to save the data, cache the data in memory before, and only write the disks right at the end. After the reduction operation, you typically have your users making use of the data. So then as we remember, we discussed those 5 architectures where the 5th was shared memory. We look at the first 4 architectures. They correspond to this: map only, classic MapReduce, iterative MapReduce or map collective, point-to-point or map communication. So these were the first 4 architectures. Actually, I called this one search before. That's because it's used for search. It's more accurately, I think, called classic MapReduce. So you have map only. You just run maps. MapReduce, you run maps and then a set of reduction operations, often just one. Iterative MapReduce is identical to this, except at the end of this step, you come right back to the beginning and start again. In the point-to-point case, you have a set of things. These could be finite elements or finite different mesh points. In that case here, the natural algorithm is local, nearest neighbor, and you need communication from any one point to its neighbors. If I'm doing a graph, we still have point-to-point, but as the graph is sort of a complicated shape, we have a more complex point-to-point communication system, which tend to be harder to parallelize in an efficient fashion. So that's what Giraffe is for graphs. MPI can also be used effectively for graphs. MPI was originally designed for things like partial differential equations and particle dynamics. Now, in the last lesson, we will start by discussing clouds and HPC, but here we'll stop. Thank you.